Okay, well, welcome to the last Rockscapes Seminar of term, and I'm pleased to say that we've got not only a fantastic speaker, but we also have the sparkling wine, as well as the normal wine. Obviously, because it's Christmas, Donna has let loose, and we've got crisps as well tonight. But it's my great pleasure to introduce Dr. Jiri Bruthans from the Charles University of Prague, who has worked for many years on sandstone and a whole range of different geological and geomorphological topics in places ranging from Iran to more locally in the Czech Republic, and has published some really fantastic stuff. So I'm delighted, Jiri, that you've been able to come over. I'm very displeased with him because he's brought Eastern European weather with him.
I'm sorry.
But apart from that, we give you a very warm welcome, and we're very pleased to listen to what you've got to tell us.
Thank you very much. Okay, so I would like to thank Professor Wills for invitation. It's a great pleasure for me to be here with you. So thank you very much. I would like to introduce the talk on rock stress, eminence degree of sandstone weathering and erosion, which will show the effect of rock stress on the weathering and erosion in sandstones. We all know that there are many spectacular landforms in sandstone, like the arches, pillars, overhangs, and pedestal rocks. And these forms obviously are results of weathering and erosion, because originally we have a body of sandstone which is carved by these processes. But there are always questions. For instance, how can erosion and weathering create such shapes, such perfect shapes? Because these shapes doesn't look like random shapes made of random erosion. They have, they are smooth over large distances. In some cases, which means that there must be something which coordinates the erosion over the whole form, because the erosion and weathering occurs mostly in relatively shallow depths. So there must be something which will coordinate the erosion to form such a smooth surface. Also, in case of pedestal rocks, you can ask how it is possible that such a rock exists which has narrow stem, large block on it, and it does not topple during the whole evolution. So how the erosion is so coordinated that it never undercuts the centroid. If it happens, the form will fail. And this must be fulfilled during the whole history of evolution. If we have thousands of them, most of them toppled. It could be random erosion. But you can see here it's just one in the middle of the desert. So there is something inside the rocks which coordinates the erosion and weathering processes, which gives the shapes to the forms. And I will try to persuade you that this is a stress, a rock stress. What it means, any matter which is composed of grains or some fragments, basically these fragments will lean one on the other, so they will make a pressure in between of the grains. We call it stress, this pressure, and the stress is thus everywhere in the landforms, in any stone, in any rock. And it's well known for a long time that if the stress will be too large, the form will fail. So everyone knows that there is a limiting, the stress is a limiting factor for the stability of the formations. And that's studied a lot. What is much less studied so far is the effect of stress on weathering rate. So not on the stability itself, but how quickly the landform will weather off. And there are many different ideas. Some authors believe that the stress is increasing the rate of weathering. Some other believe it's actually decreasing the rate. Young et al., for instance, described that the stress is able to impose a pattern, the weathering pattern. It can affect the weathering of the arches and amphitheaters. But there is one name which I should pick up, because to my knowledge he gets most closer to what you will see in later slides, how the stress actually is affecting the sandstone weathering. And that's Radek Mikuláš from Czech Academy of Sciences, who 20 years ago already published a paper in Czech language in some completely unimportant caving journal, where he wrote that sandstone exposed to considerable loading is firmer than sandstone which is subjected to lower load. It's more resistant to frost and soil weathering, and this results over time in some kind of preparation of load-bearing portion of the structure. I will try to show that exactly this is how the stress behaves. This is his cartoon, where he shows what he believes happened, because he can study just this segment, that a block changed into a block which is sitting on a pillars, and the pillars are still there because of the stress. The problem of these studies was that there were no strong evidence. So this one was completely lost, and no one took care about it. Also, the engineering geologists didn't believe that the stress can act in this way. So the purpose of this talk is to characterize the effect of gravity-induced stress on sandstone weathering and erosion, and on evolution of landforms. And I will mainly use the results of physical modeling, which is made with a special material, with a locked sand, which is material somewhere in between of sandstone and sand. Then some experiments with the cemented sandstones, and finally numerical modeling of stress inside landforms. So the material we used most is the Střelec Locked Sand. It's a material from Střelec quarry in Bohemian Cretaceous basin. This material is Cretaceous in age, and it's basically a shallow marine coarse deltas made of coarse sand. I will say more about it on the next slide. Now I just want to show you the landforms which are created within hours to weeks in the quarry. So the people do a new face on the quarry, and within few weeks you can find such a features there. You can find arches, arcades, small overhangs, pillars, which very quickly are created on the side of the quarry. So that was one of the reasons why we start to study these features. Well, you will see experiments of creation of the arches and some other stuff, but I should explain first the material characteristics, because it's critical to understand what's going on in the evolution of the forms. So this Střelec Locked Sand is basically common locked sand made of nearly pure silica grains, quartz grains, and it differs from a normal sand because it has an interlocking. So the grains has indentations which fits from one grain to the other, so they can make a firm structure. Any geologist will call this material sandstone because it can keep vertical walls. There are even natural pillars 30 meters high made of this sand. But we cannot call it sand from a simple reason, because it has no permanent cement. So it's not sandstone, it's sand. It has only kaolinite clay bridges which weaken quite much in the water. So nothing actually is cementing the grains. And due to these properties, the material has completely strange behavior. If they want to quarry the material in the mine, they have to use explosives first. it's so hard, the material, that if you will take the excavator and run against the wall of the sand, the excavator will stop, even the bigger one. You cannot scrap it much. In the same time, this material, if you will apply a water on it, it will destroy it and smash it away quickly. And it will even disintegrate in standing water. Why it behaves in this way? Because if you shear this material under load, then you have to crash the grains. The grains are so nicely interlocked that you have to crash the quartz. And that's why its unconfined compressive strength is about, say, megapascals. Unaxial compressive strength, about, say, megapascals, which is a lot for sand. On the other hand, as there is no cement in it, even very small tension break loose the material. So the tensional strength is 10,000 times smaller than the compressive strength, which is a huge difference. It has very strange friction angle, about 70 degrees, which is far more than any normal sand. And now just the demonstration what the material do. This is video made just to show the strange behavior of the material. So we have a car, we have a cube of this material which is like 10 centimeters in size, and you will see that the cube can easily withstand the weight of the whole car, even the vibration as it goes on it. If we take the same cube and we will put it to the water, it will decay in few tenths of seconds. Properties which one will not believe are possible. If you will take the jar, you will put gently the stone there and you will gently rise up the water. Once the water will hit the topmost surface of the stone, of this locked sand, it will start to decay. In a few minutes it's gone. So now, well, we can easily understand why the material is strong under the compression. But what is the reason why it decays in standing water? It took us about several months to actually make many experiments to find out. And finally, we identified that it's a slaking, the process responsible. We did many experiments with different liquids, which we were sucking into the material. And finally, we did the experiments in vacuum and compared them under the normal air pressure conditions. And what we realized was that it is the slaking, which is the process where the water is rushing into semi-dry or dry material. As it rushes into the material, it pushes out the air. But in many cases, it happened that the water is actually encircling the air inside. And the water is under capillary pressures. So it pressurizes the air a little bit, few kilopascals only. But remember, this material has no cement, so this few kilopascals is sufficient for the air to act against the pore sides. It disrupts the pore sides, I mean the framework of the grains, and everything fails. Slowly from the side to the center, but finally it fails everything. And that's the reason how it actually disintegrates, the way how it disintegrates. And we can compare this to a dry brick wall. If you have a dry brick wall, it will be easy for a person to take the brick from the very top, because there is not so many bricks put on that, so it's easy to take it out. On the other hand, it might be impossible for any person to take the brick from very bottom of a very high wall, because the friction and load is high too much. And it's very similar with the erosion and weathering processes. They actually try to expand the pore space, which could be easy if there is no friction and load on it, but it could be incredibly hard if it's loaded and locked. So that's how it works basically. It's based on very many measurements where we imposed a load, decreased a load, and measured the size of a pillar which was created. And I will show you one of such experiments on video, because these things is hard to believe until you will see the video. So there is a video which shows the similar cube as in the previous case, but nowadays, or in this experiment, it will be loaded by a small load of about 200 grams. So once we flood the cube, it will not disintegrate. Instead, there will be a pillar form. You can see that locked sand keeps vertical wall, while the loose sand is a normal sand. It never be a locked sand anymore from there. And this red arrow shows how we decrease the load. And each time we do it, the pillar is smaller. And if we stop now, it will be forever stable for months and years. But if we decrease even more, it will become smaller. And the cross-section of this form is controlled by the load, because the stress inside must be kept constant. When it's too small, it will start to disintegrate and make it smaller. So you can see that the stress is able to completely control the erosion. The erosion is just the slave of the stress. Now, if we change the experiment, there is a slight change for a man, 2 buttressing parts or 2 bases. You may say ever the same form will be formed, but it cannot be, because in the middle there is a hollow. The stress cannot go across an empty space, because any particle in the gravity field has to lean on the other, and on the other towards to the center of the Earth. So if you make a break here, the stress has to rearrange into 2 bases. If there will be 3 bases, it has to go into 3, and so on. So we have different boundary conditions, and therefore a different form will occur once we will flood this material. So you can see that if we do it in this way, there will be the arch instead of pillar. But as we decrease the load and the material has smaller mass here, the arch will change into 2 pillars which are not vertical, which are tilted. So this was arch, but now slowly but surely it will become the pillars. And then when the load is gone, the form is gone as well. So final pillars, and then immediately when the load is gone, it decays into a sand. So this demonstrates that the stress is capable to completely control the erosion, and it is the boundary conditions what dictates which form will be created. We did many experiments with the arches, and we found out that the sufficient condition to create the arch is simply to have the discontinuity inside the mass. So that's enough for the arch to form, and obviously the material has to be stress effective during the weathering. So this is, for instance, the vertical section through a block which has discontinuity in the middle. What is the discontinuity in this respect? It is any opening, 0.5 millimeter wide maybe, or wider. For instance, a fracture, or a weathered off clay horizon. Once the discontinuity is here, the stress cannot go across, so it has to avoid the discontinuity. So the stress shadow is formed there, and at this section you can see a high stress as a red color portion and low stress as a blue color. So you can see that around the discontinuity there is a stress shadow, and the stress shadow is also in these 2 corners. So once there is a discontinuity in the block, there is already the stress arch inside. And if the erosion is stress controlled, or the weathering, this arch will be preparated out of the block. Another interesting point is this is made of experiments where you have the plastic foil which compresses the whole material inside. If this is the arch and you cut small indentations here, immediately this matter is in stress shadow because the stress lines will avoid that space. So under another flooding, the arch will be larger. So to create the arch larger or expand the forms, only a very small amount of material must be removed from the critical portions. This will be common for sandstone landforms that you have some clay horizon, for instance, which is gradually eroded away because clay will not be affected by stress. So the erosion keeps continuing, and this will destabilize the surrounding and makes the form larger. From this perspective, the overhangs are basically similar forms as arches. The only important difference between arch and overhang is that in case of arch, the discontinuity propagates across the whole massif. In case of overhang, it dies out inside the massif. So the overhang is such a cavern which is not continuing anywhere. But otherwise, the shape is similar. This is another example where we left a block of Střelec Locked Sand on the roof of the building. No one touched that for 1.5 years. And you can see this is the modeling of stress in the block. You can see low stress agent here, low stress agent on the upper corners, and something like a diffuse arch here. And exactly as the stress modeling predicts, where the stress is low, the grains are not held strongly one against the other. The erosion starts first. So the stress modeling predicts quite nicely where the erosion will proceed. And finally, after 1.5 years, on a perfectly natural rain, frost, and so on, there is the arch. This example from the quarry where we accidentally broke a dam, which was damming large amount of water. So the water started to flow very quickly across the lock sand. And it started to cut down quickly a new channel. Within 1 hour, it cuts down 1 meter into the sand, into the lock sand. But one place was withstanding the erosion all the time. It was 1 meter per second full of sand grains. And this was after the next day when it was down cutting deeply. And you can see an arch. So this was the arch withstanding all the fast flow. It was before we understood what's going on in the quarry. So we tried to take this material out to understand why it's firmer and so on. And it broke into several pieces which fall down and break into the sand. It was very strong against the flow and very weak when we took it out of the structure. Well, all the experiments I showed are made under strange conditions. We flooded the material and so on. So now I will show you the evolution of the whole life of the arch from the early beginning to the end. Made in the quarry itself. So this is in situ lock sand. Only thing we did, we cut here a discontinuity because the discontinuity is necessary to create the arch. So this is drilled over a narrow space here. And there is a cut here done because if you want to study the local stress, you have to somehow cut the form out of the large stress field because the stress is going from here across that. So we try to avoid the stress by cutting this indentation. And we basically made a photograph, then we apply a watering can, another photograph, another watering can. So basically we can say that during each consecutive photographs, there will be a constant erosion. So I will play the video which shows the evolution of the arch. So you can see it's very it's going smoother and smoother, and then it will disappear and quickly disappear completely. So I will let it go the video once again, and just have a look how the form is just ugly on the beginning. There is nothing interesting on it, and finally you have very smooth shape, which is typical for these features. So the original shape and deep cutting there, which will make smooth. So you can see very nice smooth beam, and then once it disappears, it's quickly gone the whole beam out. So by this modeling, it's easy to create even the most spectacular landforms, like the landscape arch. This is last experiment with the arches, which shows once again the discontinuity here, another discontinuity which prevents the stress to come from outside. So the stress will be local here, and in the video you can see first the original shape, then the final shape, and then there will be the evolution. So at the end you have very tiny arch, and you can see once again plane form at the beginning. You can see that the erosion is quite different at different times and different places, and finally very tiny bridge. But there are obviously many forms which are affected by the stress in similar way. So one of the most important to realize whether you are dealing with a stress control weathering or not are these features, the arcades and pillars. These forms are mostly small, few centimeters in size, and they occur at many places. So there are many sandstones where you cannot find any large arches, for instance, but if it should be a material which is affected by stress, you should find such a features there. It occurs all over the earth. It occurs even in granitic rocks sometimes, and so it could be easily observed. These arcades are similar size as the honeycombs, but they differ a lot. These arcades develop along discontinuities, so they became more narrow and narrow as they go inside, while the honeycombs have obviously very flat back walls. So the difference is large between these two features. And the stress field, if we calculate the stress inside these forms, it actually appears that the stress lines perfectly follow the surface of the forms. And here at this figure there is the modeling of the original discontinuity. We took some samples of the discontinuities at which these forms are formed. Has to be obviously protected by impregnated by the epoxy first before the drilling. And you can see that the discontinuities often are segmented. So it's not open space for several decimeters or so, but instead it's open, and then there is a bridge through which the stress can go, another discontinuity, another bridge, and another portion of the discontinuity. That's the reason why you can have these pillars here. Otherwise, it will just decay completely. And so, if you see the original modeling, so you have a vertical wall, the discontinuity here, there is a high stress here, the white or the light blue, and the dark blue is quite low stress region, so that it's likely that this portion will be eroded, which is similar to the real shape of the arcades. well, this is another video which shows origin of the pillars. So here we produced artificially a segmented discontinuity. So we drilled segments here, and you will see how the erosion will proceed. And in this case, as the discontinuity goes inside the massif, and as the massif is eroded from the top, the process will never stop. It goes and goes, and it excavates new pillars. Finally, the pillars are gone, and new pillars will be formed. And you can see at the video that each time when the pillar is gone, so the stress is not transmitted across, a fast erosion phase will occur. So this is the original discontinuity, and you can see origin of narrow pillars. When the pillar is disappearing very quickly, the erosion will remove the whole space. So it goes in more and more. So originally, narrow discontinuity creates very wide erosion in wide surrounding of that point. Another experiment with the pillars, discontinuity here, and after removing the weight on the top, the erosion propagates up and down, so finally creating very nice pillars, very similar to those which are on quartzite materials in Venezuela. In this case, however, there is one thing which should be mentioned. And when we prepared this experiment, we accidentally broke this block into two pieces. It was in this stage. We tried to drill it to make a discontinuity there, and the block was broke along this line. Yet we didn't move with one part of the block compared to the other. So the indentations on one side of the block fitted perfectly to the other side. So in terms of stress, it was no discontinuity. It was still continuous, even if it's two blocks now, perfectly fitting one to the other. And you can see that as this joint was still transmitting the stress, the erosion did not excavate this joint along, but instead propagated up and down. So these pillars are actually cut in the middle by a joint, yet the erosion doesn't care. A very nice example of such behavior is a Burda bridge in Wadi Ram. That's a bridge spanning like 20 meters across a heavily jointed zone. So the bridge itself is composed of many blocks separated by joints, yet the erosion is excavating nicely the bridge, and it doesn't care about the joints. So this shows an important thing, that the joints might be important discontinuities affecting strongly the stress, but they might not be important at all if the stress can be transmitted through them. But it's not only about the effect of stress on intensity of the weathering and erosion. The stress can nicely coordinate the erosion in the way that it's able to produce such a cupping stone sitting on a very narrow stem. So something similar to pedestal rocks from the desert. In this case, the experiment was done in the way that originally here we had the block, which was loaded by a large amount of lead loads, and we were able to separate the erosion into very many events. So we flooded the block to some level, then we put the load out, we flood it again, put another load out, and so on and so on, finally leaving just the sandstone cap on it. And so each event was eroding a portion of the material, and finally you have a stem which is 20 times smaller than is the cap. What this means actually, it's out of random completely. Under random erosion, always the erosion from one side will be faster than from the other. So what it will do, it will undercut the centroid and the form will fail. What happened instead in case of these forms? From the side where the erosion is fastest, it actually starts to topple a little bit towards that direction, which makes stress higher from the direction, which makes easier for erosion from other side to keep pace. And finally, the form simply regulates the erosion from all sides to get in similar time towards to the centroid. That's the reason why we have such a nice stones. It's not a random feature. When we produced this, we were just shocked, and we were aware that it cannot survive anything, so we have to destroy it anyway. So we put two measures there, and we start to move with the form a little bit until it crashed completely. And this is about 30 centimeters high, and we were able to move it few millimeters. So this is not, it's extremely easy to be destroyed, but it's not rigid. You can move with that a little bit. So it's not plastic, it's flexible, this material. Now, obviously the locked sand is very rare material, or not very rare. It's not so common as the cemented sandstone, but you can find it actually at many places, at least 3 places in the Czech Republic. And I just wanted to show an interesting place in South Africa, close to Coombes, where exactly this material can be found in the caves. It's a portion of a black reef quartzite, which is incredibly old, 2.2 to 2.5 billion years, so extremely old material. There are large caves with perfectly rounded ceilings, and if you take a piece of the material, it behaves exactly the same as in Střelec. So you can put that material to the water, keep compressed fingers, and then after a moment you will produce the pillar in your hand, which is another nice proof that it's a locked sand. Very clear proof that there is a big difference whether it's compressed or not on the erosion. Well, all these experiments were done just with the locked sand, with a material which immediately is eroded, and with the water erosion. We obviously did the experiments also with the cemented sandstones, because most of the landforms are created in cemented materials. So we took samples from different formations in Czech Republic and also in the United States at Colorado Plateau. We cut the 4 centimeter cubes from that, and we always use 3 cubes which were without any confinement, and 3 cubes which were inside of a steel frame. These were compressed to about 1 megapascal, so relatively large stress. And then we apply a salt weathering on them, and also for some other cubes the frost weathering. And you can see the difference. These not loaded cubes, which are in blue, for many lithologies survived much longer time, much smaller number of weathering cycles than the loaded cubes. Not for all lithologies, but for many. So there was a difference. And what is maybe even more interesting, it produced often the pillars. So you can see a nice pillars made by water erosion if you compress it from the top to the bottom. And you can see the same shapes made by salt weathering. So what this tells us, it shows that actually the weathering or erosion process is not important in shaping the landforms. It is the stress field, its boundary conditions, what shapes what will be formed actually. Similar result was with the frost weathering. Here you can see the unconfined cubes and the loaded cubes. Once again, the loaded cube survives longer. And in some cases much longer, like in case of Aderspach, which shows one of the nicest morphologies in sandstones. So it seems that the stress affects many different weathering processes in similar way. But there is a big difference. The water erosion in locked sand is stopped completely if you keep the load. If you decrease the load, like in case of the small arch, it will never stop. But if you will keep the load, it will never go further. In case of salt weathering and frost weathering, you will never stop the process. The process will still continue. The probable reason is that the slaking is working with much smaller pressures inside the pores, so they can be stopped completely. In case of salt and frost weathering, the pressures are high too much, so they are slowly but surely disrupting the structure. And it's just a question of time when they will completely destroy the form. Well, the very important point is, however, that to erode the stone has to be weakened so much that it will simply be washed by the water, for instance, or it will just fail as a grains down. So we should not look differently too much on the locked sand compared to cemented materials, because finally the cemented material is decemented often or broken into pieces. So there were done measurements of tensile strengths and other parameters on the Colorado Plateau sandstones, for instance, where we have very firm material on the beginning. And you can see at this graph, and you can measure it in many other places, in Petra and other places, that the tensile strength, which is extremely important, is dropping down orders of magnitude. And we never measured the tensile strength below 1 kilopascal, but that's because the rain will take the material or it will fail the material under its own weight. So it can go, and so the firm rock could be very strong material, but you should not forget that in the field finally you will have the material which is very similar or equal to behavior of the locked sand. So even if there is not a big difference in weathering rate by a salt of a firm material, it doesn't necessarily mean that the process does not operate in the nature. So I believe that the best way is actually to do not use for the testing whether it's stress affected material or not, to do not use a firm material, but rather use some weaker material from the field, because it's already weakened by the real processes, and you can distinguish, you can get the behavior more closer to reality. Quite recently we get first results for a full-scale conditions, because so far all the experiments were done in smaller scale. It was not full-scale landforms. In full-scale landforms we have a problem that mostly the erosion is running too slowly, so we have to wait too much to get some measurable data. We are lucky for one overhang in our county which is decaying very quickly. That's because a sewage water gets into it and it weakens the material quite quickly, so that we were able to put the plastic packs into that and to measure the erosion rate on the overhang. The maximum erosion rate is about 30 millimeters per year, which is incredible rate. You can see here amount of matter which fall during the winter, so it covered the grass completely. The photographs were made of the overhang. A three-dimensional model was produced from the photogrammetry, and the stress was calculated inside the overhang. And you can see a low stress regions and even the tension inside the overhang in blue and white color. You can see the high stress regions in red, yellow and white blue color. And the erosion rate has the indirect relationship with the stress. So the place where the erosion rate is highest has also the lowest stress, or it's even in the tension. So once again, it works here, the phenomenon. But obviously, the forms I mentioned are not the only material which is affected by the stress. We can nicely demonstrate these effects on the landforms, but it should affect any weathering of such material. So, nice example of effect of the stress on weathering of culture heritage is a Petra site. In the Petra, most of the monuments, or nearly all of the monuments, were created 2 millennia ago, 2,000 years ago, and they were basically rectangular in shapes. Nowadays, these forms are remodeled into such a pattern, and when we took the samples there, cut the cubes and tested the cubes under different amount of load. So not loaded and unloaded, but increasing load. There was a decrease in weathering rate as the load was increasing. So at this site also the stress is important. Yet, surprisingly, the stress is not yet much considered in case of culture heritage studies. It's not important only for the monuments carved in a sandstone continuous body. It also, in some cases, you can see it even in walls which are made of blocks. This example from the Czech Republic, from one wall a few hundred years old, where they used quite a weak material, and you can see the arch there, and you can see the arcades as well, quite commonly. So it may affect also the walls in some cases. So in the Petra, after 2 millennia, originally rectangular shapes were changed into these shapes, which are very typical for this kind of weathering, that you have a narrow pillars. The pillars can survive for a long time because they are stabilized by the load. So the narrow pillars are typical and quite important feature to identify the stress erosion weathering. And here is just the experiment, the physical modeling with the Střelec Locked Sand, showing that originally the rectangular shapes can easily be remodeled into such a shape. So we can see actually a 2 millennia of weathering in Petra, say, due to using this material. So you can see origin of very narrow pillars, and once the pillar is gone, a very fast erosion of material above and below, because the stress is gone from that place. There are many examples which could be shown. Just very recent stuff from our country. There is a mine in kaolinite-rich locked sand. No one calls it locked sand. It's just called kaolinite sand. And mining engineers were quite surprised in the past that the mine is still intact. You can see scarps after the pits which they made this underground galleries. And that's surprising because this mine was several times flooded by water. So you will expect it will fail into loose outside the mine on the surface. There are no outcrops of this material, nature. It's just washed away. There is a grass and trees growing on this. So how it is so stable? Well, because the miners in that time were able to produce nice parabolic passages. They probably did it not only because of the stability, but it's more easy to produce such a shapes than to carve inside the material. These parabolic passages respect the stress lines, and the material is stable. Even if flooded, we can demonstrate it quite nicely. If we drill a core of this material, we can wrap it into a common wrapping foil so that the material is stressed about 10 kilopascals. That's enough for the material to survive with a perfectly vertical wall underwater. So this is photograph of the material flooded. If you cut the foil, or if you will put such a core without a foil, it will immediately disintegrate into loose material. So once again, the stress is able to stabilize the material for a long time. If there is a lake in this material, outside lake, it will decay quite quickly, which is the case. So one should understand the behavior of this material, because it's something which is not obvious. Well, so to conclude, the behavior of this processes, all what I was showing is a single mechanism. The stress is capable to control the erosion and weathering, and so the load-bearing portions of sandstone mass will be eroded and weathered more slowly, so they will finally dominate in a major sandstone landscape. And in the same time, the non-loaded parts, which we can call ballast, are eroded quite quickly. That's the reason why we have so nice forms, because it's basically a load-bearing portions. And that's why the forms are so stable, because anything which is actually not necessary, it's very quickly eroded away. So you should not think on sandstone landforms as it is some stupid piece of rock, because it's very far from how the system is actually behaving. You should rather think on these landforms as it's billions of sand grains which are making an array, a body, interconnected body, where the stress interconnects everything into a single body. And the landform actually is regulating the erosion on its surface. That's how it is. Obviously, the landform knows nothing about itself. It's no intelligence in it. It's simply a very simple feedback. What is loaded is more protected than what is not loaded anymore. And we have only several boundary conditions which can occur, and each boundary condition will create a different form. And we have already names for such a form. So we can call this weathering and erosion a stress control weathering. And this stress control weathering creates different forms, which I already mentioned. but each form has its specific boundary conditions. Now, very important are the discontinuities, because the discontinuities are separating or dissecting the stress field into segments or into different domains, or how to say. So even a very narrow discontinuity can control the erosion well above and well below its place. This is from Czech Republic, the example where you have a shallow clay horizon, yet the erosion of the sandstone is affected 15 meters above. So the sandstone here is not more weak than the sandstone here. We could be sure with that because it was just transported from a dune or from a delta. So it's basically the same on the top as on the bottom. The erosion is faster here because we are closer to the discontinuity. At Colorado Plateau, there are the best examples of this. We have shallow discontinuity, few decimeters wide, yet the sandstone is more eroded 50 meters above and 50 meters below the discontinuity. So the discontinuity is extremely important control on the whole erosion in far above, far below. And another important point is that the discontinuity is often whether at a rate which is not controlled by any way by the stress. So it keeps rotating, and that's why the whole sandstone above and below has to keep rotating as well. So last example of the experiment from the quarry, basically homogeneous material with a cut which should simulate this discontinuity, and you can see that the erosion is strongly affected, and basically this discontinuity controls the whole shape finally. So you can see that finally the original discontinuity is not visible, but we have indentation here. So if we will come to such a place, we will probably say, well, this is a weaker sandstone. It's much weaker than this one. No, it's because there was a discontinuity. So that's maybe the most important thing, that as the stress field strongly affects the weathering, any discontinuity in the massif will make much faster erosion. And yet the sandstone can be just the same here as here. So you always should look on discontinuities if you study the weathering progress, because you can get a false view that the sandstone is weak. It may not be the case. Well, the important question, what created the landform shapes? Was it erosion or the stress field? Obviously both. Without erosion, there is no change. Without stress field, there is no nice landforms. But we can put this question slightly differently. What created a statue of David? Was it chisel or was it Michelangelo? And obviously, both were very important, because no man can carve the statue in the marmor by his hand. There's no way, or by the teeth. It will be impossible. So any person has to use some tool. And however, no one is saying that a chisel is a quarter of a David. It's just the Michelangelo. Why? Because the chisel can do anything itself. If the person cannot touch the statue, cannot do nothing with the chisel either. And the most important thing, the Michelangelo can use many different tools to create the same statue. He can use a driller, for instance, if it will be invented in his time. And it will be very similar statue. And using this analogy, actually, The gravity-induced stress will be the author of a sandstone landforms, while erosion and weathering will be the tools. And this analogy is important, or it's interesting in the perspective that as the man producing the statue can use many different tools producing similar landform, similar statue, the stress also is capable to use many different weathering and erosional tools to produce a similar shape. So we can actually simplify the processes if we will distinguish 3 different things. First, the stress, which is interrelating all the factors into a single process or single system. However, the stress itself has no shape, it's shapeless. It's just bounding the things together, just transferring the information, the stress field. It needs some boundary conditions, and the boundary conditions dictates what will be created finally. We can see it on the model of the stress on the original shape to know what will happen. So the boundary conditions are dictating what will be created. Stress is making the relationship between all the processes, and the erosional and weathering factors are working hardly at a given space, producing the forms. And I believe this distinguishing these 3 elements of the system is important to more easily understanding the whole system. So, is it just the sandstone where we can see these forms? Actually, not. We can find similar forms in some brechas, where the material weathers between the portions of the breccia. We can find it similar forms in nodular limestone, where the limestone nodules are separated by clay coatings, one from the other. So this looks like a sandstone. It's a Devonian limestone, actually, from Czech Republic. But the best after sandstones are the granitic rocks, the weathered granite. Why? Because the weathered granite material is once again a locked material where the grains are fitting nicely one to the other. So we have a nice arch here, it's in Wadi Ram, in the granite, which is on the base. So we basically believe that any material which has interlocked structure, and in the same time it decays into blocks or grains. It might not be the grains itself, it might be even blocks, which are, however, fitting nicely together. Any such material is able to produce nice landforms. The double door, for instance, if you get close enough, you can see that it's also made or it's decaying into fragments, smaller fragments which fits nicely together. However, the sandstone seems to be the best material, and the reasons are probably the quartz and its properties. Most of sandstones, especially those which produce nice landforms, are made of quartz from large decay. And the quartz is a special mineral because it's very firm, very resistant to any erosion and weathering. And compared to other minerals which are common on the Earth's surface, it has one big advantage, and that's that it actually is dissolved and reprecipitated in quite a large scale over the existence of the formation. So most of sandstones have strong portion of reprecipitated quartz in it. So the grains are no longer oval grains randomly sitting one on the other, but mostly they have long contacts where we have these indentations. And because the whole frame of the sandstone material is made of quartz, the important elements, it could survive for a very long time. Second reason is that sandstone has appropriate size of pores. So if we have much more fine material, the pores will become small, and the pressures inside the pores, crystallization pressures and other things will become so large that they will destroy the material. So the sandstone is just the perfectly balanced for this flow cube. So, well, so it seems that the stress control weathering is something real, but obviously this is just it's just small digging into a topic. So far there are just physical models which can show the evolution of the landforms. But the physical models have many limits. For instance, we cannot apply a watering from the can to very special places. The water always will flow along the gravity down. So to exactly reproduce the located salt weathering is impossible by this approach. So it will be nice to create the numerical modeling of these processes, so where you will not only model the stress distribution in the form, but the stress distribution will affect the erosion rate, and the erosion will affect the form, which will in turn affect the stress modeling. It's hard to do this because of the computations, but also because of the necessary input information, which is the function between the stress and the erosion rate. So we have now the grant project which is focused on this, and I would like just to show a short video of Arch. It's very simple, not still working much nicely, but this is video which doesn't show the stress itself only, but it shows the effect of stress on the erosion, and it's a loop. So the erosion removes the material, which affects the stress again. So you can see where the stress is high, where it's low, and finally it produces something close to the arch, which is nice because in the nature you never know, in the physical modeling, whether you really understand what's going on. You never know whether it's the process you believe it is, or it's something else which behaves in the same way in this aspect. In the numerical modeling, you exactly know what the model is doing because someone has programmed that. So we can be sure that if it works in the numerical modeling, it's something real. And so I arrived to conclusions. So this, to my knowledge, this is for first time when the sandstone landforms were created from the real material and by processes which are close to those which operate in nature. And the spectacular landforms could be created by this. So we believe, based on this, that it's something real and it's something important, something which should be taken into account, the stress inside the landforms. As I told, increased stress is keeping the material stable, which is against what the engineering geologists are often believing. However, these stress intensities are very small compared to maximum stress which can the landform survive. And for these landforms, the negative feedback between stress and erosion is probably the defining principle, which is responsible. So we can, in my opinion, call these landforms stress control, and the weathering stress controlled weathering, because the stress is a central point in that. And under given boundary conditions of the stress field, different weathering and erosion factors creating the same shapes. So the stress should be, in my opinion, taken into account in case of weathering, because in some cases at least, might be quite important. So I would like to thank you for your attention, and thanks again, Professor Wills, for inviting me. I acknowledge that a lot, that I could be here with you today.
Thank you.